Surface water level instruments. Water level measurement plays an important role in water resources management. In case of reservoirs, lakes and other water bodies, water level is used for determining available storage. In case of flowing rivers and canals, the water level represents flow rate. There are several common methods to measure water level. Each method has advantages and disadvantages, along with the cost for purchase, operation and maintenance. There are two types of water level sensors: contact type and non-contact type. In non-contact type water level sensors, level is measured from a height as distance between instrument and water surface. In contact type water level sensors, the instrument is in direct contact with water and the water level is estimated as thickness of the water column above a reference level by measuring pressure exerted by the water column on the instrument sensor. A more modern approach to stage measurement has been introduced with ultrasonic and radar distance measurement sensors. And if it is feasible to move the site to nearby bridge, these are preferred. Ultrasonic distance measuring sensors are comparatively inexpensive. The sensor measures the distance of target objects, that means water surface, by sending pulsed ultrasound waves at the object and then measuring the time for the sound echo to return. Knowing the speed of sound, the sensor can determine the distance to the object. The operator needs to know the exact elevation of the sensor and then subtract the distance to the water from the elevation of the sensor to arrive at stage. The ultrasonic measurement of water level is one of the most sustainable approaches to measuring water level. It is a non-contact method of water level measurement, which means that what flows in the water and any water pollution will not interfere or otherwise foul the sensor. The limitation of this method is that you need to make this measurement directly over the body of water being measured, which is not practical in reservoirs or rivers that have shallow slopes. The ultrasonic measurement is also a narrow-range sensor, limited to 10 meters in most applications. It is more ideally suited to canal measurements. The measurement is generally unaffected by the transparency, reflectivity, opacity or color of the target. Objects can be measured from 0.5 centimeter to 15 meters from the sensor. Disadvantages are that you need some structure to mount the sensor, a bridge railing or a boom, and the measurement is not as accurate or precise as other measurement techniques, usually being within 0.1% of full scale. This accuracy is generally sufficient on small bodies of water, such as creeks and small canals. In the event a larger distance needs to be measured or greater accuracy is desired, a radar sensor is available. The radar sensor improves the accuracy to approximately 0.03% of full scale and has a maximum range of up to 70 meters to the target. The advantage of using radar is the non-contact nature of the measurement along with high accuracy together with the extended range of measurement over the ultrasonic. The radar is also relatively easy to install. Disadvantages include the high cost of radar, along with the need for something to mount the radar on, such as a bridge structure. In contact type water level sensors, we have shaft encoder, bubbler and pressure transducer. The most common method of measuring water level is a stilling well equipped with a float and shaft encoder. The components for this type of gauge, including a stilling well, inlet pipes from the water, float, tape, wheel and shaft encoder, which electronically sends signals to the data collection platform. The civil works for this type of station is among the most expensive, while the sensor and associated equipment is among the least expensive sensor solutions. The stilling well requires occasional flushing to remove sediments that may have collected at the bottom of the stilling well. If left unchecked, the sediments could eventually block the inlet or outlet pipes. This sensor never needs to be calibrated, but only checked and reset to an outside staff gauge. A staff gauge that covers the entire range of water levels is necessary to check the measurements of the shaft encoder. The staff gauge is basically a ruler that is placed permanently along the shore or on some other structure. The staff gauge is used to compare to the reading of the shaft encoder, allowing the operator to correct the shaft encoder to the staff gauge. A visual comparison between staff gauge reading and the data collected by the data collection platform is made during every visit to the gauge station and recorded in a log book, which should be placed at every gauging house. The staff gauge has two sections, conveniently placed for easy readings and easy installation. Some staff gauges that are in rivers or reservoirs may have numerous sections to cover a large range of water levels. Staff gauges are often damaged during flood flows, but fortunately are relatively inexpensive to purchase and place in the water. Staff gauges should be surveyed after high flows to assure the debris has not damaged the staff gauge or otherwise altered the indication of the water level. Another method of stage measurement is the bubbler system equipped with a non-submersible pressure sensor. This is also known as a gas purge system. A small quantity of air or inert gas, for example nitrogen, is allowed to bleed through a pipe or tubing to an orifice in the stream. The pressure of the gas that displaces the liquid in the orifice is then measured by a pressure sensor. The main advantages to a gas purge system are that this technology does not require a stilling well and the large associated cost of installation. Another advantage is the sensor is not in contact with the water, which means Any debris in the water won't cause damage to the most expensive part of the bubbler system, which is the pressure transducer and compressor. Many manufacturers now produce compressors with tanks to store the compressed air for the gradual release of air into the orifice line. The equipment can conveniently operate with a small 12 volts battery that is charged by solar power. The main disadvantage of this system is the cost of the pressure transducer and gas compressor storage system. The desiccating system that is normally needed to keep water out of the compressor system is a recurring maintenance item. Bubbler systems work well in open channels as well as reservoirs. Another method to measure water level is to use a submersible transducer. In this instance, a transducer is installed in a pipe below the minimum water line. The pressure exerted on the sensor by the head of water above the sensor is converted to depth. The main advantage of a submersible pressure transducer is that the sensor requires the simplest installation, as the sensor only needs to be run down a pipe to some level that is lower than the expected minimum water level. The submersible pressure transducer is also one of the lowest cost sensors for water level measurement. The main disadvantage is the sensor is in contact with the water and all debris in the water. In the event of a flood, the debris in the river can sweep the sensor away. These sensors are more susceptible to damage caused by lightning striking the water and also need calibration that usually requires the sensor to be sent back to the factory. A submersible transducer should be avoided in open channels and is more appropriately used in wells to measure groundwater or in lakes, where the occurrence of damaging debris or toxic water is not an issue. A common problem with submersible transducers is evident when installing the sensors in lakes. Lightning that strikes the lake can damage the sensor if the sensor is not properly protected. There are manufacturers that warranty their sensors for the life of the sensor to lightning strikes if you employ the proper grounding techniques that they provide. To summarize the main points of surface water level instruments, the selection of appropriate instrument technology depends on site conditions, presence of existing infrastructure, example, stilling well or bridge, desired accuracy, range, distance to the water, sedimentation rate and cost of the instrument.